because these models are huge, we are talking about hours or days of processing time before we can actually evaluate this design. With physics AI, we can enable an alternative workflow. That model doesn't even have to be located on the designer's PC. It could very well be on the cloud. In terms of geometry, we're looking at the coordinates for the points that form that geometry. We are looking at the connectivity, and we also have certain optional inputs such as part labels. In physics AI, there's no need for explicit parameterization. For example, if you look at different geometries where the variation is very organic, you can't necessarily put parameters on them. Testing a model is something that shouldn't be restricted to a single numerical value. You have to look at a couple of factors.
Again, another deep dive session, ladies and gentlemen. I'm incredibly excited to have Shubham today on the deep dive session with the topic of physics meets AI, geometric deep learning with Altair's physics AI. Quick introduction, we take a closer look at how Altair's physics AI can be deployed to make fast physics predictions on new designs and CAD models. Physics AI's intuitive user interface enables users like yourself, regardless of their data science experience, to create powerful machine learning models for extensive design space exploration and performance optimization at a fraction of the cost and time typically associated with iterative FEA or CFD evaluations. But I think before I do any more introductions, Shubham, let's just delve into it and let's get started.
So, hello everybody. Start my presentation. So, Physics AI is a platform for building AI models for CAE. And the idea here is to bridge the gap between data science and CAE. It is, we don't need data scientists to use AI. And that's the beauty of physics AI. It just simplifies the process of, deploying and creating AI models for CAE applications. Now, underneath physics AI, we use a geometric deep learning engine to understand the patterns of the results, so we can directly learn on 3D meshes using your past simulation data, and we deliver fast physics predictions on new designs that come up during the design process. So since we use deep learning, we can apply this method to different domains. We are not only restricted to structural CFD, but we can cover a wide variety of different applications, right from electromagnetics to aerospace, healthcare, and you name it. So how does physics AI differ from traditional machine learning? So surrogate models, which usually are regression models, usually have a set of parameters, that means numbers going in, and we fit some sort of regression equation in there, and a KPI or a key point indicator value, which could be a single number, comes out. Now, if you look at the way this is constructed, these parameters need to be explicitly created, and because they are defined for a fixed set, there are a lot of restrictions in terms of the variety of inputs that it can adjust. For example, if there are additional parameters, you can't combine old data with the new data and create a combined regression model. You would have to rerun and create an entirely new surrogate model. Also, the output that is coming out is usually a single value, or in some cases, a vector or a curve. Contrast that with physics AI. In physics AI, there's no need for explicit parameterization. For example, if you look at different geometries where the variation is very organic, you can't necessarily put parameters on there. But physics AI, with its geometric deep learning engine, is able to accommodate that variety, which traditional surrogate models can't. In addition to that, we also have a mechanism to input explicit parameters. So there's the implicit geometrical variation, but also some explicit numbers that can be added to the input set. And on the output side, not only can we predict those scalar values or the curve predictions, but we can produce full 3D fields for the results. For example, a displacement or a stress plot. And we can even train physics AI to predict some custom outputs, such as the failure modes. whether it's buckling or some other kind of deformation pattern. So really, it's physics AI can work with the larger subset of the input and output types. So I spoke about the geometric deep learning engine, but what is it that physics AI uses to process this variation? So in terms of geometry, we're looking at the coordinates for the points that form that geometry. We are looking at the connectivity, and we also have certain optional inputs such as part labels, which come in. For example, if you want to differentiate between different parts in a certain finite element model, for example, you could have a bracket and a pin, and you could differentiate that, or maybe rigids and deforming geometry. Additionally, to input certain parametric inputs, we have a method called custom inputs. Now, through this mechanism, we can put in features like thicknesses, materials, or it could be any other useful input, such as maybe an inlet velocity or an applied force. And on the right hand side, this data is processed and spit out in the form of nodal or elemental results to create the 3D full 3D representations of fields. And we can even predict certain custom what we call vectors, and those basically represent the scalar values and the KPI and the curve values. So that's a brief introduction to physics AI. Now let's see physics AI in action. So to demo that, I'm going to use HyperMesh, which is our pre and post processing utility, and also our model visualization tool. Physics AI is embedded inside of HyperMesh, and I'll talk about how well these two technologies complement each other to create an integrated tool. So let's say a designer has created a new design, and they have created a CAD model. So I'm going to drag and drop that car model in here. All right. So if you look at how a traditional workflow proceeds, designer creates a CAD model and then hands it over to the CAE team. Now the CAE team has sort of a manual and labor-intensive task of taking this model, meshing it up, applying boundary conditions, loads, and then solving it either using a CFD solver, because in this case we are going to evaluate the drag coefficient, or if it's a structural problem, then a finite element solver. But because these models are huge, we are talking about hours or days of processing time before we can actually evaluate this design. And obviously, there's not going to be a single design evaluation. So you can imagine how the required time adds up. Now, with physics AI, we can enable an alternative workflow. So now, instead of having the CAE team manually set it and run the simulation, they can use past simulation data because they have similar designs in the past, and they can apply physics AI's geometric deep learning engine to train a physics AI model that can predict the drag performance, for example. And that model can now be directly shared to the designer, and they can produce fast physics predictions to get an evaluation within a few seconds or minutes. So that model doesn't even have to be located on the designer's PC. It could very well be on the cloud. So let me show you how that would work. For example, in this case, this is Altair One, which is our cloud platform for sharing files and deploying Altair appliances. As you can see, there is a folder here called Physics AI Models, and inside which pre-trained physics AI models have been uploaded. So think of it as a CAE team uploading them to the cloud and then sharing it with the designer. So in order for me to make a prediction, I need to first create a project. So let me go ahead. And by the way, this is what we call the Physics AI ribbon. I'll talk more about it, but for now, let me just walk you through the demo. So I'm going to call it car prediction. And then I need to specify a location where this should be saved. So I'm going to select this folder and hit OK. Okay, you can see that the project name is reflected right next to the author. Now, I'm going to import that model, which is available on the cloud. So I'm going to model training and then importing a model. And right here, you'll see the integration with Altair OneDrive. So I'm going to click on that and hit fetch. So we have two-factor authentication. So bear with me for 30 seconds while this loads up. Okay, so now you can see the list of all the models that are shared with me or available to me on the cloud. I'm going to select the last one and just set it as active. So that model will be downloaded and we will activate it. Okay, it has been set to active. And I have the CAD model, I have the project, and I have the Physics AI pre-trained model loaded. All that remains to be done is now to hit predict. So in less than a minute, we have an evaluation for a complex model, and we have both a scalar response and a field prediction. So in this case, the wall shear stress on the car body, and then the average coefficient of drag for the vehicle. So you can imagine how much time savings now are achieved for the organization as a whole, because the manual tasks on part of the CA team is reduced, and they can investigate their other methods. Maybe it saves them some time. And from a designer's perspective, they can evaluate a lot more designs. They can come in and make minor geometric modifications to the car, for example, increase the width, increase the height, and use the same model again and again, and very quickly evaluate multiple variants of this design. So let me show you another example, this time for a transient use case. So for that, I'm going to use a hood impact case. So let me drag and drop it in here. Okay. This is a radius deck. So this time I'm going to work with the mesh. Okay, as you can see, this is the front hood and there is an impactor. Now I'm going to repeat the same procedure. So going to project and let's call it hood impact demo. And I need to save this project, so I'm going to save it here. Now, going to model training and retrieving an appropriate model from Altair 1. So this time I'm going to select a different model, set it as active. Go. And now I'm going to hit predict. So within a few seconds, we should see, a transient prediction for the deformation. And let me turn on the transient simulation. I'm going to turn on the deformation here. And let's reduce the speed a little less. And here you can see that for a completely new design, it is able to predict the deformation pattern because of this impactor landing on the hood and then bouncing back. Now, if let's say I want to evaluate a couple of different variants of this impact case. So maybe the impactor is moved a little bit, and I want to see what the deformation looks like for that case. So that is very easily done by interacting with this. So let me first use this move tool in here and select the impactor. And then I'm going to click on move. So move a little bit in the X direction and then a little bit in the Y direction. And let me switch to the top view to show you the difference. And now I'm going to hit predict. And you can see that the impactor location has been updated and the changed deformation pattern is now reflected in the prediction. So, orders of magnitude faster, and the predictions are very good. We do have a metric here, which is a similarity score that indicates how novel this design is to the training data, and that can be correlated to the accuracy or the trust that you can have with the prediction. So I showed you how the physics AI models can be deployed. Now let me walk you through the process of creating this physics AI models. So let me create a new session here. Right. So I spoke about how physics AI is to enable the creation of AI models without having to be an expert at data science. And to do that, the tool has been constructed in such a way that if you look at the icons in this ribbon, it's kind of a self-guided tour of where do you start with, what are the steps you need to follow to create a certain physics AI model, and then validate it. And then once you're happy with its performance, then you can go and predict it or maybe share it with the designer. Um, so let's start with one step at a time. Let me first show you the starting point, which is the past, existing simulation data, either from past studies or maybe if there isn't sufficient data, then you can always run a design of experiments. So in this case, I have all my files saved in a folder called iBeam dataset. And the type of files in here are number one, an H3D file, which is Altair's native result file format. Then we have a FemDeck, and then we also have a JSON file for bringing in some custom inputs, something like a curve prediction or a scalar prediction. So I have 33 data points, and each data point has three files. The advantage of Hypermesh is that it can not only support Altair's native file formats, but also other third-party file formats. So we are pretty flexible in a variety of data that we can use for this particular process. But step zero in creating a physics AI model is always to first make sure that you have sufficient data, and in the absence of sufficient data, you can generate some synthetic data. Okay, so first step, as it says, is to create a project. So I'm going to call this training demo project, and then it is asking me a location where this should be saved. I'm going to save it here. All right. So the next step is now to create data sets or import them somehow. So right now, since this is a new project, there isn't any data set. There is an option to import. So just the way that I imported models from the cloud or some local directory, you could do that for data sets as well. But let's go ahead and let's create a new data set. So I'm going to call it IB, and it's asking me for the directory where the data is stored. So it's an IBeam data set. Now inside this folder, I have filtered out all the H3D files. Let me go ahead and select all of them for now, and I'm going to add them in the dataset creation tool. There are some check boxes at the bottom, but I'll cover them later on. Let me first go ahead and just create a brute force data set. Okay, so now you see in the upper table there is a data set appearing called IB, and it shows me that there are 33 files contained within it. In the table at the bottom, there is a summary of all the data points inside this particular data set. So, for each of the data points, you have the file name, run IDs, nodes, elements, and then certain KPIs. For example, the max stress value or the min stress value for certain load cases, or you could even look at the displacement values. So you can see that rows 2 and 9 are highlighted in red because this had been flagged as outliers. Maybe because the KPI value is not matching. For example, for row 2, you can see the subcase 1 max displacement value is orders of magnitude higher than the rest of the points. Same for row 9. And that's also the case for subcase 2 element stresses. So when we create data sets, we want to make sure that there aren't any outliers that introduce noise or skew the performance such that physics AI is not able to make accurate predictions for the general design space it's supposed to perform in. And because this is in Hypermesh and it's a preprocessor and a model visualization tool, very quickly I can actually take a look and see why is this an outlier. For example, I selected row 2 and I clicked on display file, and now I can see that it's like a curved ribbon, whereas if I look at row 1, for example, it's an IB. So maybe the dimensions for row 2 are like so far off that it's not a useful data point. So that's something that needs to be eliminated. And because there's this information available here, I could even manually scan this and flag more outliers than what physics AI suggests. For example, I think row 7 is also an outlier because the displacement magnitude is a couple of orders of magnitude higher than the rest of the data set. Okay, so the next step is going to be refining this data set or curating it to remove all the outliers. So I'm going to create a new data set called IBeam curated. and again point to the same files. I'm going to add all of them again just because it's easy to add 33 points and then remove the ones I don't want. So 2, 7, and 9 have been removed. You can see that the selected files are down to 30. Now, let me come down to these check boxes at the bottom. So the first one is enable train test split. So in physics AI, or in data science in general, we want to make sure that the AI model isn't overfitted to the training data and it's generic enough so that it can work in the entire design space. And one way to do that is to reserve some data that is available for testing. So you don't show that data during training. And then once that model is trained, you test it on unseen data. If it performs well on the unseen data, you know that the model is generic enough to perform well in the entire design space and not just on the training data. So you have this option to take the initially available data and split it at the beginning to reserve some data for testing. So I've set it to 90%, but the user has the choice to change it to 80, 75. It all depends upon how many data points they have available, and each problem in a way is unique. But reserve some data, and majority of the data should be used for training. Then we have the extract solid faces check box. And this is useful, let's say, if you're not really interested in the results inside the model, but rather just on the surface. So you can save some computation power by checking this box. In this case, it doesn't really make a difference, but because these are all elements. And then the last one is extract simulation properties. And this is useful for parsing out some parametric inputs such as thicknesses and materials. So in this case, thickness is a variable. So I'm going to check that box. And now I'm going to hit OK. Should be done in about 30 seconds more. Here we go. So two more data sets now appear in the top table. The IBM curated test with 3 files and IBM curated train with 27 files. And now if I look into these, there are no outliers. So that's how I know that these are good data sets to use. All right. Coming back to our ribbon, so we completed the second step, which is dataset creation. Now I go on to the third step, which is model training. Again, there's no models because this is a completely new project. I'm going to click on create model. So the first field that I need to enter is a model name. So you're going to have multiple models, so it's better to give it a very descriptive name. So I'm going to call this displacement and IY, which is the moment of inertia along the y-axis, and maybe add some hyperparameter values. We'll see what those are. So let's say I'm going to call it disp IY 50. Then the next field here is a drop-down menu from which I can select the data set that should be used during training. So obviously I want to use IBM curated training. Now it shows me a list of all the available inputs for this file. So coordinates, it's the default one. That's how the geometric deep learning engine can actually process the geometry. So that should be checked. And the only other variable is the shell thickness. Now, there are 2 more inputs that I could check, but if if a variable isn't really a variable, if those values aren't changing across the samples, there's no point supplying it. So I know that materials are not changing across the samples. That's why I've not checked it. On the right hand side, you can see outputs. So there are two types of outputs. One is vector, which is the KPI, the curve value, curves, etc. So you can see that the data available for this data set in particular has a few KPIs, but I'm interested in the moment of inertia along the y-axis. So I select IY. The second type of output is a contour or a full field a response. So I'm going to select displacement, but I'm free to select as many responses as I like. Of course, keep in mind that the more responses I ask it to predict, I'm asking physics AI to juggle or trade off the accuracy. So it's better to not select too many, but a few is fine. Then you have to select the architecture. So physics AI currently has two architectures. First one is graph context neural simulator, and the other one is transformer neural simulator. I won't get into the details because that's get into a very big topic. For simplicity, let me select the first one, which is the GCNS. Now, based upon which architecture you select, the hyperparameter values or the tuning settings basically are displayed. So for example, for GCNS, you can see that there is width, depth, batch size, and epochs. So these are essentially controlling the settings that should be used during training, and how should the fitting be done, etc. The default parameters are more than sufficient for this simple problem that I'm demoing. But if there are more complex problems, the user can easily come in here and edit them for for their preference. I want to show a quick demo, so I'm going to reduce the number of epochs to 50. By doing that, I know that the model is going to be kind of a bad model. It's not very well fit, but I just want to show how it works. So let's set it to 50. Then we move down here and you'll see a checkbox for transfer learning. So this is a very useful feature. For example, let's say that you have created multiple physics AI models and you have a new design come in, but you don't want to start from scratch. You can say, I have these physics AI models that are lying around and there's useful information contained within them. I want to retrieve some of that information or use that as a starting point. That can be done through this transfer learning feature. You have to check this and then you'll have to point to the pre-trained model. So we'll not do that in this demo, but that feature is in there. So you're not wasting away your past models. You can still reuse them. The last option here is to specify where you want to run these, run the training. Now, you can run it locally, and it helps a lot if you have a GPU. We've seen a speed up of more than, I feel like, more than a factor of 10 with GPUs. And it doesn't have to be a high-end GPU. Most laptops, they have very good GPUs, and that should be sufficient for most physics AI cases. But there is also an option to submit this training to Altair One or to the user-specific HPC platform, right? So I'm going to stick with local and hit train. So you can see that the model training, it was processing and now it's running. And if I want to keep a track of what's happening, I have two utilities. The first one is a text log and the other one is a loss curve. So inside the text log, you'll see a summary of all the files that were used, the architecture that was used, the hyperparameters that was the values that were specified during training. And then once the training starts, you can actually see the mean square error loss value, and you can track how well the model is performing. Notice that there are two curves in here, the training loss and validation loss. So in order to avoid overfitting, we have actually reserved some of the training files to kind of keep a track of how generic the model is, or to avoid overfitting. So I have a GPU on my laptop, and you can see that in less than a minute, I was able to run 50 epochs for this model. All right. Um, and if you look at the log, it also summarizes the best epoch. So Physics AI remembers the best configuration or the best training round of epoch. So you could run it for a really long time if you're not sure how long to run it, and then Physics AI will automatically, cut back to the best epoch it encountered during training. All right. So the model is trained now, but I need to make sure that the model is actually a very good model before I can hand it over for field deployment. So the penultimate step is model testing. And right now there's no test scenario, but I can create one by clicking on the test model button, and it shows me a list of the available model. Right now, there's only one, and then the data set that should be used for testing. So let me select IBM curated test, because this is the data which is unseen during training. Okay. So the testing for each of these models is going on. Now, the difference between testing and prediction is that in testing, you have a true value to compare to. So each of the points in the test data set has an FE result. And that's how I can compare how well my predictions are vis-a-vis the FE result. Okay. So testing a model is something that shouldn't be restricted to a single numerical value. For example, I can't just say that, there's this MAE value, the model's good enough. It has to be a little more holistic. You have to look at a couple of factors. For example, if you just focus on the MAE value, there is an MAE value for each of the response, so displacement and the IY, or the moment of inertia. As for the set as a whole, that's displayed here. But then if you look at the table at the bottom, there is an individual MAE value for each of the response per data point. So test data point 1 has a displacement of MAE of 3.01 10 to the power negative 4, and then IY value, MAE value, and so on for each of these. So you need to look at the overall value, and you also need to look at the individual MAE values. It could be that one of the error values is okay, but the other one's too high, and that value needs to be relative to the scale of the results. So there needs to be some, a detailed inspection of these results. The other factor is we also need to look at the distribution. So we can do that by selecting a data point. Let's select the first one and clicking the display file button. And that will show us a true versus predicted, Physics AI predicted versus FE true results. So you can see that the predicted results are not too shabby, but they're not good enough, right? Clearly, and this is what we expected. The model is, a very quickly trained model. It's not going to be very accurate. And the field results, true versus predicted, are shown on the right hand side. But for the scalar, which in this case was the IY value, the moment of inertia value, That's plotted on a graph with the true value on the x-axis and then the physics AI prediction on the y-axis. So if the prediction was perfect, the point would have been along the 45-degree diagonal. So point one looks okay, but you can see that two and three are kind of far off. And if I actually switch to let's see, let's do run ID 2, the results may be a bit different. So that's why it's important to look at this in a detailed manner and not just rush looking at this one value. So let me take a snapshot of this because I am going to contrast it with a well-performing model. So let me go back to model training and import a model I had trained before. So I know that it's in here. So the file format for physics AI model is .psmdl, and I'm going to give it a name of pre-trained model, and let's import it. Okay. Now to make an apples to apples comparison, I need to test this new model against the same data set. Okay. Now look at the MAE numbers. Clearly, these are in an order of magnitude lower than the previous model. So I can preliminary, just looking at this numbers, I can say that this is going to be a better model. But let's not stop at that. Let's also look at how the predictions look. And now if I compare it, clearly you can see that the first model had very jagged predictions, whereas in the second one, it's much more smoother. Right? So that's how I know that model 2 is a better model to use than model 1. And, if as a user proceeds with their training, they will see that certain models are not very well, are doing very well. So they can do some hyperparameter tuning, they can adjust their data, and then keep comparing with the same benchmark. And finally, when they're satisfied with the performance of the model, then we move on to the last step, which is prediction. And that brings me back to the beginning of this demo, where we saw that we can just load in new designs and use our pre-trained models to make predictions very quickly. So that brings me to the end of this physics AI demo.
Shubham, thank you so much. It was really, really cool to see that. One of my most favorite deep dive sessions for sure. I've seen there was also a lot of interaction. I'm not sure if you've seen it on the site, but in the comments, people were like they asked a ton of questions, and luckily Fatma and Eamon were taking care of the answers. So thank you for that. A couple of questions I have is what makes the geometric deep learning models uniquely suited for simulation tasks compared to the traditional approach of ML models?
Right. So it's a very good question. If you look at the amount of variation that the geometric deep learning engine can handle, it's orders of magnitude higher than what the traditional regression models can handle. For example, most of these parametric studies have restrictions on, like, the mesh has to be the same, the parameters cannot change. You can't have one data set with like 3 parameters, another one with 4. You can't combine them. Whereas with physics AI, you can actually do that. The other thing is with regards to the types of outputs that we can produce. You saw that we could produce full 3D predictions of this, and not just static 3D predictions, but also a nonlinear or transient simulation where you see parts deforming, and then maybe there's some elastic recovery and so on. So that's something which traditional surrogate models cannot handle.
Thanks. How can we ensure that physics AI models are trustworthy? I mean, you covered it a little bit, or like quite extensively actually in the deep dive session, but how do you usually approach this topic of trustworthiness?
Right. And it has to be, again, an extensive exercise, I would say, to make models which are really trustworthy. First of all, we need to decide the scope of them, scope of that. Like, what does that exactly mean? We have to think about the design space in which they will be deployed. And then the training data has to be a good representation of that design space. And so does the testing data. So you train these models and then you test on the test data set. If it performs really well on the test data set, which is very well distributed in that design space, you know that the model is going to perform well throughout that design space. So it takes a little bit of trial and error because every problem is unique. There's a lot of factors. The geometries change. There could be different parts, or it could be a transient problem or a static problem. So depending upon each use case, the exact number of test data points can change. But as long as you have a good representation of the design space and it performs well in testing, so if you compare the true versus predicted for the test data set and those results are good, you are guaranteed to get a good prediction.
That's great. Okay. Last question from my side. How do you handle the trade-off between accuracy and the computational efficiency when you apply this geometric deep learning to more complex simulations?
Yeah. So clearly, there are going to be, there are certain good practices that should be followed. For example, you can't expect physics AI model to first create something out of nothing and to predict everything. So if you have like 10 responses across 8 load cases, that's not a good, it's not a good objective to ask physics AI to predict everything in one go. So you have to keep it focused. Of course, you can always increase those hyperparameter values, but it is directly constrained by the memory available to you. In case you're not able to produce a good model in a single go, what you could do is maybe use transfer learning, or take out parts of the model which are not required. For example, let's say if you got an assembly of 20,000 parts, but you're really focused on 2 or 3 critical parts, and the other parts are not really contributing so much, like bolts and nuts. So you can remove those and really keep a razor focus on the objective.
Great. I think with that, Shubham, we can wrap it up. Again, very, very excellent demonstration. I really loved it. And there's over 50 comments in the comment section. Maybe you can check them out after the deep dive. But again, if people want to check it out, I also posted the link to Physics AI in the chat. It's altair.com/physics AI for people who want to get more information on the whole Physics AI topic. Again, Shubham, thank you so much. Hopefully there will be a second part in the future, and speak to you soon.
Thank you, Yusuf. Thank you all.